Well, see, this is a viral equation of a state, and this equation used to determine the intermolecular potential. Potential means intermolecular force, right? So basically, this equation is written as a compressibility factor as a polynomial of reciprocal of molar volume. So this equation you can write here, the viral equation of a state, or this equation this equation expresses the compressibility factor, expresses the Z as a polynomial of of 1 by V bar, right? Polynomial in 1 by V. V bar. So we can write here Z is equal to PV bar by RT is equal to 1 plus B into T by V bar plus C into T by V bar square plus dash, right? So this is the viral gas equation in terms of what? Volume. This is equation 1, right? And in terms of pressure, we also write Z is equal to PV dash by RT. This is equal to 1 plus B dash T into P plus C dash T into P square plus equation 2, right? So basic equation, fundamental equation is this. This equation is this equation is derived from this. So B and B dash, see here what is the meaning of here writing of T. So this B or B dash, it is called second viral coefficient. C or C dash, this is called third viral coefficient, and 1 is the first viral coefficient here. So these are the coefficients, and basically value of which depends on the temperature, right? So B or B dash is called second viral coefficient, second viral coefficient, C or C dash is third viral coefficient, right? And B or B dash or C dash, or these viral coefficients, basically they depends only on temperature, independent of density the gas or any other factor. So these coefficients B, C, R depends on temperature. Temperature. This is very important point, right? So, and what is the relation between B dash and B? So you can write here B T is equal to RT into B dash, right? Simply see here, if you put here equation of state V dash is equal to RT by P, so here you will get RT and P here. So R and T is constant. So B by RT is equal to basically B dash. So you can simply write this relation in terms of pressure. Basic equation is this: polynomial of polynomial in 1 by B. Right? So how this equation is useful to explain the behavior? Wait few minutes, you will automatically get how this equation is beneficial. Now see this magnitude of this second virial coefficient B in whole equation. Most important coefficient is this B, and this B is negative at lower temperature, and it will increase as the temperature of the gas is increased, right? So at low temperature, at low temperature, low temperature, the value of the value of or the B is negative, or even C also. B and C are negative, and increases with increases with rise in temperature, rise in temperature. So obviously when this B and particularly I am talking about B, second viral coefficient. So if value of this is B is negative, so on increasing temperatures, when B is increased, so at some particular temperature the magnitude of B becomes 0. You know, that is very important point. The temperature at which the temperature at which temperature at which the B is 0, at which B is equal to 0 is called Boyle's temperature. Boyle's temperature. And you know, when B is 0 in this equation, when this B is 0, and these higher terms are negligible, because you see here this is V square, V cube, and so on. So these terms are very less in magnitude. So what will happen? What will happen here? What will happen? these terms are insignificant and this becomes 0. So in this situation, what will happen? Your behavior of the gas is ideal. So here you can write at Boyle's temperature, what will happen? The force of attraction balanced by force of repulsion. Force of repulsion means gas behaves ideally at Boyle's temperature. Right? Force of attraction balanced by the force of repulsion, that is gases behaves ideally. Gases behaves ideally. Right? So at Boyle's temperature, the force of attraction and force of repulsion are what? Balanced, and in this situation the behavior of the gas is ideal. So Boyle's temperature, the temperature at which the behavior of the gas is ideal, or second viral coefficient becomes 0 in the viral gas equation. Right? Now see, we can explain or we can find out the formula for Boyle's temperature in terms of van der Waals equation. So van der Waals equation can also be expressed in terms of this viral form. See how P plus A by V bar square into V bar minus B is equal to RT. Right? So we can write here P is equal to RT by V minus B minus A by V bar square. Right? So we can write here PV is equal to PV by RT is equal to from here we can take V dash out. So what is left here? 1 by 1 minus B by V bar. Right? Minus A by RTV bar, this form, and this is equal to, we can write Z, so this equal to, we can write here 1 minus B by V bar power minus 1 minus A by RTV bar. Right? So now we can write this in the binomial expansion. We can write here. So Z is equal to PV bar by RT. This is equal to 1 plus B by V bar plus B square by V bar square plus B cube minus A by RTB bar, right? So now we can write here plus dash 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 minus this. So this is equal to 1 plus B minus A by RT 1 by V bar plus B square by V bar square plus dash dash dash. So this is equal to, if you compare this equation with this viral gas equation, then you can find out that second viral coefficient B is equal to B minus A by RT. This is second viral coefficient, and second viral coefficient C is equal to, sorry, this is second viral coefficient, this is third viral coefficient is equal to, this is equal to B square, correct? And B is equal to this. So the most crucial is this: if higher terms are insignificant here, so if temperature at which this becomes 0 is called Boyle's temperature, so when T is equal to TB, then B is equal to 0. So we can write here 0 is equal to B minus A by RT, right? So or TB is equal to A by RB. So this is called Boyle's temperature. So now you have two temperatures, Boyle's temperature and critical temperature. 8A by 27 RB and Boyle's temperature is A by RB, right? So this is the Van der Waals equation. Van der Waals equation in terms of viral gas equation and calculation of Boyle's temperature in terms of A and B. So critical temperature and Boyle's temperature. If one temperature is known, then you can calculate the other temperature, right? So this is very good equation or very fundamental equation through which you can explain the Boyle's temperature, and you can find out the temperature when the force of attraction and force of repulsion between the gas molecules are balanced, right? One more temperature is there, that is known as inversion temperature. Inversion temperature. See, inversion temperature, this is represented Ti, right? So inversion temperature is the temperature, it is defined as the temperature above which gases shows heating effect, and below which cooling effect in in Joule-Thomson's effect experiment. Thomson's experiment, right? And this Ti is equal to 2A by RB, 2A by RB, right? So now you have inversion temperature, you have Boyle's temperature, and you have critical temperature. So see, Ti inversion temperature is 2A by RB. Boyle's temperature Tb is equal to A by RB, and critical temperature Tc is equal to 8A by 27 RB, right? So I think 8A by 27, so this is 0.29A by RB. So this is the maximum, highest. Then this, and then this. So the inversion temperature for any given gas, this is highest. After that, this Boyle's temperature, and then this critical temperature. Means gases behaves ideal slightly higher than critical temperature. Slightly higher than, because it is what value this was? This is 0.29, yes. So this is 0.29 A by RB, and this is A by RB. So this value is larger. So slightly higher temperature, at slightly higher temperature than critical temperature, gases behaves ideally. So these are the different terms which are used to explain the properties or behavior of real gases, right? See, this is one question based on this viral gas equation. Evaluate the Boyle's temperature in terms of the known constants A, B, and R for a gas having the equation of state is this. Suppose that this equation of state is given for any gas. So you know Boyle's temperature at this Boyle's temperature, the second viral coefficient is 0. So identify from this that which one is the second viral coefficient, right? From this equation. So we start with your basic equation, viral gas equation, PV by RT. Z is equal to PV by RT is equal to 1 plus BT by V bar, right? This is your basic equation. Now transform this equation in this form. So you can write here PV bar is equal to, multiply this RT here, or you can multiply RT through RT with the whole to the whole equation, RT plus BT into RT by V bar. So you can write this RT plus BT, and RT by V bar you can write P, right? So this is equation 2. So compare this equation with this equation, so you will find the second viral coefficient. So the second viral coefficient B is equal to, BT is equal to, by comparing these two equations, you can write B minus A by R into T to the power 2 by 3, right? And you know, at Boyle's temperature, at Boyle's temperature, B, this is equal to 0. So you can write here 0 is equal to B minus A by RTB to the power 2 by 3, right? So you can write A or A by RTB to the power 2 by 3 is equal to B. So TB to the power 2 by 3 is equal to A by RB. So TB is equal to A by RB to the power 2 by 3, right? 3 by 2. This is 2 by 3, na? So here 3 by 2. So this is the answer. Okay. So in this way you can find the Boyle's temperature in different terms. Okay, now one question I am giving you as a homework to you people. Try to solve this. There is no any solution kind of question, just knowledge based question is this. Only true and false you have to identify here, true and false, right? So this is homework. Identify true and false. First statement, say with respect to this figure, true and false with respect to the given figure. For given figure. First is x, y, x is here gas, y is liquid, and z is liquid gas. Second statement is x can be converted, x, state x, state x can be converted to state y, at temperature D and pressure F. Temperature D and pressure F. Now C part is below temperature C, below temperature C, state X cannot exist. State X cannot exist at any pressure. At any pressure. Right. D part, X can never be converted into Z. State X state Z cannot be converted into state Z only by increasing pressure, only by increasing pressure, increasing pressure at a temperature above C. At the temperature above C, above C, right? So try to answer all these questions in terms of true and false, right, with respect to this figure. Okay, so this is the question. See, this is an additional point here. This is also sometimes IIT-JEE advanced people, they may ask the question. See, intermolecular forces, when molecules, gas molecules are treated as a hard sphere. So when molecules are approaching to each other, when molecule approaching to each other, when they approach, some potential energy developed between this, right? Potential means potential energy. Potential energy is developed. Energy is developed. So regarding this intermolecular forces, Leonard Jones has suggested two parameters. The name of the scientist is Leonard Jones. Leonard Jones suggested two parameters for this potential energy. One is sigma. This is called molecular diameter or molecular cross section area, or you can say it is directly proportional to or relate the molecular diameter. Just means it is related to the size, basically. Molecular diameter. And other parameter he suggested, is epsilon. This is the depth of the attractive well. Depth of attractive well. basically this parameter is responsible for repulsion, and this is for attraction. So this results the repulsion, and this is the consequence of attraction. So how this attractive well and this repulsion, how we can explain this potential? Simple graph, all of you are knowing that graph. See, this is the potential, and this is the separation between two gas molecules, potential energy as a function of distance between the gas molecules. So this sigma, this is the I mean zero, no energy, no attraction, no repulsion. So this sigma is the, I mean this, so in this case only one parameter is there, and this tells about the distance from this sigma. So when a gas obeys this equation of state, PV minus B is equal to RT, then this potential energy can be expressed like this, in this form, right? Because there is no force of attraction, then your graph will not go down here. It is a simple graph, as you know, we have plotted that Z versus P like that. Here we are trying to evaluate the potential energy, and this equation is given by Lennard-Jones equation, known as Lennard-Jones equation, but it is not required for you. Just its result I am discussing here in terms of van der Waals equation only. So if your equation, any gas obeys this equation of state, the potential energy is given by this. Only repulsive. See here, repulsive forces are there. There is no attraction is there. Similarly, if your, potential well, if it is represented like this, see, we are, so right, so this type of graph you may get when your gas obeys. So this depth is represented by this epsilon, right? And this is sigma. Sigma is basically here in the Lennard-Jones equation is the distance from here to here, this distance, and for gas to gas this distance is different, right? This distance is sigma, and this height is the depth of this potential well is this epsilon, right? So in this situation you have only this, both attractive and repulsive, both forces are there. So equation of state is like this: P plus A by V bar square, V minus B is equal to RT. Means when attractive and repulsive both forces are there, then your potential energy variation is like this, right? See here, this is attractive force, and this is repulsive force, so here attractive and repulsive both forces are present, right? So this equation, if only repulsive, then your potential energy variation is like this, right, with the molecular collision. So this is the interpretation of this van der Waals equation of state in terms of force of repulsion, potential energy in terms of potential energy, right? So this is just interpretation, not more than this is required, not required that you go through this Lennard-Jones equation and write and remember that, right? Okay. Now see, this is a question. Z for a real gas is this: at 273 Kelvin and 100 atm, calculate the mass of gas required to fill the gas cylinder of 100 liter. See, one way to write the equation for real gas is not only every time if Z is given, so you can write PV is equal to Z nRT, right? This is equation of state for real gas, equation of state for real gas, in terms of Z, right? We have already used this equation. So P is given, V is given, Z is given, and R and T is, R is constant, T. So you just put the value here and get the answer, don't worry. So P is given 100 atm, volume is 100 liters, Z is a dimensionless, that is 0.927. Into this moles, you can replace mass of the gas required by this 30, right? So this you have to take this 30 grams per mole. Unit of this is multiplied by R, 0.0821 liter atm per mole per degree Kelvin, and into temperature 273 Kelvin. So Kelvin to Kelvin cancel, mole inverse to this cancel, atm to atm cancel, liters to liters cancel. So we will get mass in gram. So if you solve this equation, you will get W is equal to 14.4 into 10 power 3 gram answer, right? So in this way you can solve this equation question, such type of question. One more question. See, for 1 mole of a van der Waals gas, for 1 mole of real gas, B is equal to 0, and T is equal to 300 Kelvin, right? PV versus P. See, PV versus P. I should show you the plot because in writing it will take so much time. P versus 1 by V plot is given. See, this graph is given, and what find the value of A, van der Waals constant A in what is the unit of this? ATM liter square per mole square. ATM liter square per mole square. So find the value of A, right? Find the value of A. So B is 0 given, and temperature is given 300 Kelvin. So if B is 0, so how to write the van der Waals equation for this? P plus A by V bar square into V bar is equal to RT. So this is the reduced form of van der Waals equation when B is equal to 0, right? It is clear. Now if we can write here PV is equal to RT minus A by V. Already we have done this, right? So here the graph is given between PV versus 1 by V. So PV bar, this you can take Y, and this we can write this like this: A into 1 by V bar. So this we can write X, this we can write M, and this is C, right? So PV versus 1 by V graph is given. So now this is very simple. Now slope of this curve is equal to minus of A, right? Slope is minus of A. So slope is equal to, we can write 21.6 minus 20.1 divided by 2 minus 3. So this is equal to minus 1.5, right? So A is equal to 1.5. See, 21.6 minus 20.1 and 2 minus 3, right? So by this we can calculate this value of A, right? So in this way you can determine the van der Waals constant if a graph is given, right? Okay. Similarly, sometimes it is asked what is the ZC. This is called critical compressibility factor. What is the value of ZC, right? So all of you are knowing that PV is equal to Z and RT. In the critical form you can write here PC VC is equal to ZC and RTC. put the value of PC, VC and TC and get the value of ZC. So PC is equal to A by what, 27 B square. What is PC? A by 27 B square. PC is equal to A by 27 B square. VC is equal to 3B is equal to ZC, and we can take N is equal to 1 mole, so R here, and TC is equal to 8A by 27 RB. So R cancel, this B is square cancel, B cancel, A cancel. So ZC is, and 27 cancel. So ZC is equal to 3 by 8. 3 by 8. Right? So sometimes it is asked, what is the value of ZC, critical compressibility factor? So you can calculate in this way. Okay, and one more law is there, law of corresponding state. Although it is not required for you, but I will discuss. See, the reduced equation of state or law of corresponding state, we can say. So reduced temperature, basically TR is equal to normal temperature if divided by critical temperature, right? So T by Tc. Similarly, reduced pressure, this is called reduced pressure, reduced temperature. Simply reduced pressure, PR is equal to P by Pc. Similarly, reduced volume, VR is equal to V by Vc, right? So if we substitute all these values in van der Waals equation, then we will get the reduced equation of state. Cp plus A by V bar square V minus B is equal to RT. So in place of P, we can write PR into PC. PR into PC plus A by V bar square. So we can write here VR into VC, VR into VC is square, right? And this is equal to VR into VC minus B is equal to R TR into TC. Now replace this PC, VC, TC in terms of van der Waals parameter. So we can write here PR and PC is equal to A by 27B square minus A by VR and VC, VR square, and VC is equal to 3B square, and VR 3B minus B is equal to R TR and 8A by 27 RB, right? So this R and R cancel. Now if you simplify this equation, finally you will get, I'm writing here final equation, PR plus 3 by VR cube, no, VR square. right? And 3VR minus 1 is equal to 8 TR. This is called reduced equation of state. And you know, in this equation, if you see, you will find that this equation is independent of the nature of the gas, right? In this, there is no A, there is no B, there is no capital R, nothing is there. Only PR, VR, and TR are there, and some numerical values are there. So this reduced pressure or reduced volume, all these terms are independent of nature of the gas. So this is also, for every gas, this temperature or pressure is same. Reduced pressure is same for every gas at given volume and given temperature. It will not depend on the nature of the gas, right? So this is one method to express the reduced form of the equation. So it might be possible that at some place you may find some question and they have asked this, what is this reduced pressure and what is this reduced volume, right? So in this way you can calculate. If you know the critical temperature and normal temperature, so you can evaluate the reduced temperature for that gas. Okay, good. Now this topic is, this chapter is over.